probability of B. So you can clearly see this relationship here. Then we can have another condition whereby the probability of B given A, where A has occurred already, is the probability of B intersecting A divided by the probability of A. So once again, making the probability of B intersecting A the subject of the formula, this will be equals to the probability of B given A times the probability of A. And if you notice, I tend to combine the two results because going back to the special results, that the probability of A intersecting B is the same as the probability of B intersecting A. Give me a break. Hello? What happened? Yeah, quick, because that's an online class right now. I do online and I'm not supposed to me. Give me a break here, class. 1 minute. Okay, let's go back. So looking at the special result, like I had mentioned to you, and we can combine because knowing that the probability of A intersecting B is the same as the probability of B intersecting A. So we equate these two expressions and we obtain that the probability of A given B times the probability of B is equals to the probability of B given A times the probability of A. And you will find this result to be quite useful shortly when we look at solving particular problem. So that is when it comes to conditional probability. Now, when it comes to independent events, like what we were saying, we can have two or more events happening at the same time. However, they do not affect each other. So you could be flipping a coin and tossing a die at the same time, and one event will not affect the other one. So in the case of independent events, we mentioned that the probability of A given B is equal to the probability of A. The probability of B given A is equal to the probability of B. And that the probability of A intersecting B is equal to the probability of A times the probability of B. And remember that we have used that formula to have solved some problems. Then we also look at exhaustive events, whereby we have that A union B is equals to 1, whereby all the elements has been used up in this particular set. Are there any questions? Are there any questions? Hello, are there any questions?
Sir, I
Yes.
have a question. Like, why do we use like multiplication in the independent events, and then in like the first ones that we were doing, we use like addition instead of
No,
like.
because that was a different, when we were looking at mutually exclusive event, which I didn't place here, mutually exclusive event is dealing with or A or B. Mean A or B, which is the union. And then we have that the probability of A union B is equal to the probability of A plus the probability of B for mutually exclusive events. So that's the reason you saw that was. I remember I also mentioned for mutually exclusive, the intersection is zero. There are no such intersection. The intersection will be zero when it comes to an
Yes, sir.
exclusive event. Okay?
Yes, sir. Thank you.
So for the exhausted event, you need to know the fact that the probability of A union B is equals to ones. So which means that you have used up all the given members of those particular set. When combining them, it gives you the whole, which is one. So last time we looked at various problems in which I have not sent them to you as yet, but by this weekend everything will be sent to you starting from today. I'll be sending some of these information in order for you to keep up with the work.
Yes, sir. Thank you.
Okay, you're welcome. Okay, let's look at question number 17. In fact, let's look at question number 20 before we get back to 17. How would we attempt that question? It said two tetrahedral dice with faces labeled 1, 2, 3, and 4 are shown, and the number on which each land is noted. The score is the sum of these two numbers. Find the probability that A, the score is even, given that at least one of the die land on a tree. And B, you need to find the probability that at least one die lands on a tree, given that the score is even. So what I want you to do is to start listing the possibility space here. I will give you like 3 minutes to do that before we attempt the question, because you must remember when we did it with two die, ordinary die, you have 36. The sample space was 36. Now, these are tetrahedral die, which have four faces, and there are two of them. So drop the possibility space. And remember, they're asking about score. The score is the sum of these two numbers. So if a 4 pops up on one tetrahedral die and a 3 pops up on the other, that will be a score of 7. Right? The score is the sum of both. Okay, students, I'm back. Let's look at the different possibilities here. So remember, we need to draw a possibility space diagram. Okay, so we have di1 and di2, both of them are tetrahedral. So So the first one would have been, remember, if you get a 1 and a 1, that would be 2. A 1 and a 2 will give us a sum of 3. This will be 4. And this will be 5. Can you hear me, students?
Yes, sir.
Okay. So what will be the sum? This will give us a 2 and a 1. This is 3. Then 4. This will be 5. And that will be 6. The other one here will be 4, 5, and this should be 6, 7. So this will be a score of 5, 6, 7, and 8. So our NS in this case will be 16. So those are the possibilities. That is the possibility space diagram for the two tetrahedral dice with faces that are labeled from 1, 2, 3 up to 4 are shown, and the number in which each line is noted. The score is the sum of these two numbers. Find the probability that the score is even, given that at least one die lands on a tree. So at least one die lands on a tree. So you could either have this possible one die land on the tree, and we have this sum, and we have the other one land on a tree, which would be this one as well. Like I said, at least one of the die land on a tree. So both of them can land on a tree. And since it's two die, either one can land on a tree. So it said here, find the probability that the score is even. They want that the score is even, given that at least one die So what's the first thing we need to do here?
Wouldn't we identify the even numbers, sir?
Okay. So first of all, what we need to list then?
The even numbers.
The event, right? So we can say let E represent. Remember, we have to state some events. So E will be what event here? That the score is even. And what else are they talking about here?
That it is a tetrahedral dice.
Yes, but the other thing is said the score is the sum of these two numbers. Find the probability that the score is even given that one die lands on a tree. So they're talking about the tree here. So we can let let's say that we can have f So what type of probability is that? Find the probability that the score is even given that at least one die lands on a tree.
Isn't it conditional probability?
Yes, it is conditional probability, but yep, it is conditional probability indeed. So how can we write our formula in terms of those two events, E and F? So how can we gonna write the formula?
Using the multiplication rule, sir?
Remember, let me take you to this again. Okay. Is probability of A given that B has occurred. This is how the first one reads. And then the second one, the probability of B given that A has occurred. So in terms of E and F, then how can we write this formula?
Sir, wouldn't it be like the probability of F that E has occurred?
Let me see if that's the first one is saying here that the score is even given that at least one die lands on a tree.
Sir?
Uh-huh.
Sir, can you hear me?
Yes, I can hear you.
Would it be that of like P open bracket E close bracket times P F's and the slash close bracket?
Okay. Probability of open bracket.
E.
Yes, E given that F has occurred. So that will be I don't like that symbol there. I don't know why it's giving me that bar. right now. That will be E intersection F over the probability of F. So the score is even and it's land on a tree. So how much that will be? What that will be? It said that the score is even because here, even and it's land on a tree.
Sir, the one that lands on a tree wouldn't be like 8, sir, because adding the numbers that would land on the tree would be 4, and the other one, the die number 2, would be a 4 as well. So adding it will give you 8.
Okay, the score is even and it's land on a tree. So if you notice here, what will that happen is land on a tree. It's even and land on a tree. And this an even score and it's land on a tree?
No, sir, it will be 4 because it's only 2 of them that are even there. Like in each 3 columns, sir. I know.
Yes, but how about 6? This number, isn't this even? And it's land on a tree too? I remember I said at least one land on a tree. So we could get both trees as well. So indeed, you have 1 here, we have 2 here, and then we have another 1 here. So that would be 3 out of what?
3 out of 8.
Why 8? What is the sample space, the possibility space?
I mean 3 out of 16, sir.
Okay, so you're gonna be 3 out of 16. Okay.
So one question. So when you're adding the how you mean the even numbers, you're not going to like count 2 times, right? Like I was counting it like in the first die, I was counting it like 4 and 6, and then the second die 4 and 6 again. So that's why I told you it was 4.
Okay. So it's 3 because if you notice, this one is for both of them. And remember when we we are doing something like a union, putting sets together, we cannot repeat the elements. It's only
Okay, sir. Okay, I got it. Thank you.
okay. So that is what is happening there. So that will be 3. So let's finish this here. And then what will be the probability of it's landing on a tree?
It wouldn't be like 5 out of 16, sir?
So remember, it's land on a tree, and we have 2 dice, so we have different here. So it's gonna be 1, 2, 3, 4, 5, 6, 7, 8.
Yes, sir.
Because I just say it's one of them is 2 dice, so each one of them have a label 1 to 4. So if we have die 1 be stationary, that let's say remain on a tree, the other one could be a 1, which gives you the 4. The other one can be a 2, which gives you, so the possibility will be, well, the probability there will be 8 out of 16. You got that?
Yes, sir.
So let me copy this here. And let us put in some numbers. So what did we obtain for E intersecting F? The score is even and it's land on a tree. We said that was 3
Out of 8, sir.
out of 8. 3 out of 8 or 3/16? Look like that 8 might clear tonight. It's it's 3/16.
Yeah.
And the other one, since we are multiplying because it would be a fraction as well, we mentioned in order for us to land on a tree, it will be 8 out of 16. So we're gonna reciprocate that. Which should have been 16. Now remember, we have converted the division sign to multiplication. So we reciprocate that fraction that is there. So what would be our answer? For that part, what would be our answer there? The answer is looking right at us.
3/8.
3/8. that is probability. Remember, probability has to be between 0 and 1 inclusive. So this is a function that falls between 0 and 1. So the probability of E given F has occurred is 3/8. Now, how would you do for part B? Because part B was, it said at least one die. Right? At least one die lands on a tree given that the score is even. So what will happen to this formula here? Let me see if you are reading properly. All we need to do is to shift this around. The probability of F given E, which will be the same here. This could remain the same, which would F intersecting E is the same as E intersecting F. And then here, and then this would be the probability of E here. Then we go back to the table and get our information. So our class has almost come to an end. So what you can do, when I send this there, I want you to find the other part of this question, which would be the probability of F, given that E has occurred. The one that we did here is the probability of E, given that F has occurred.
Okay, sir. Sure.
Okay. Well, enjoy the rest of the day and make sure you have a safe weekend. Enjoy your weekend. Remember social distancing. Practice good hygiene. Enjoy.
Yes, sir. Thank you, sir.
Okay.
Same to you, sir.
Okay, you're welcome.
Okay, bye, sir. Thank you.
Okay. Bye, everyone.
Bye, sir.
Okay, bye.